Hello everyone, it's 1 p.m. Eastern Time, and that means it's time to begin another of our monthly CoCoRaHS Weather Talk webinars. Thanks for joining us today. Hi, I'm your host, Henry Regis. Behind the scenes with me today, running our technical side of the program, are Zach Schwalbe and Noah Newman. And joining me today is my colleague, CoCoRaHS founder, Nolan Duskin. We're coming to you live from the Colorado Climate Center here in sunny Fort Collins, Colorado at Colorado State University. For those of you who are unable to join us for our live broadcast, we'll be recording this one today for future viewing on our website. All of our Weather Talk webinars are sponsored by grants from NOAA's Office of Education and the National Science Foundation. Well, we've got a treat for you today. Today's webinar, we're going to take a look at how NASA studies Earth's climate, weather, and hydrology from space. And we have two guests here on with us today. We're excited to have Dahlia Kirschbaum from NASA's Goddard Space Flight Center in Greenbelt, Maryland, and Eric Conway, who's at the Jet Propulsion Laboratory in Pasadena, California. Eric is a historian at the Jet Propulsion Lab. His duties include research and writing, conducting oral histories, and contributing to the lab's historical collections. Dahlia is a research physical scientist with hydrologic science at NASA's Goddard Space Flight Center and currently serves as a global precipitation measurement mission application scientist. Boy, it's a mouthful. I'm sure she'll be telling you more about that and what that entails during the presentation today. Her research interests are centered on natural hazard assessment using remotely sensed information, focusing on rainfall-triggered landslide hazard assessment and modeling. Boy, does that sound familiar. Wow, what a timely subject as we're taking a look at what just happened over the past weekend just north of Seattle. Well, welcome, Eric. Welcome, Dahlia. It's great to have both of you with us today.
Thanks. It's great to be here.
Thank you so much.
Okay, well, we're going to pass the baton here to Eric, and we should be seeing Eric's screen here in a moment. It should be coming up. Okay, well, bear with us a second. Just click on that, Eric. You got it? There we go. Excellent.
Okay.
All right, take it away, Eric. Thanks for joining us.
So first, I want to thank Dahlia for inviting me to do this last week. I don't get too many opportunities to give a short presentation to a public. Once upon a time, I was asked to write a history of NASA's role in the development of atmospheric science in the United States, and a big part of that was its meteorology program in the 60s and 1970s. So that's what I'll be talking a little bit about today. I just want to point you out to the picture in the corner of this slide. This is what was this was the first dedicated geosynchronous weather satellite known as SMS-1, built by Goddard, the synchronous meteorological satellite, and actually was about the third one that carried a camera for photographing the Earth's atmosphere from geosynchronous orbit. So where did all of these things come from? Well, one of the big origin stories of weather and study of weather from space actually is a crew called the Rocket Research Panel. It was actually supported by the Defense Department from between 1946 through about 1958, used sounding rockets to do high-altitude research. And some of those experiments were aimed at gathering cloud photographs in the hopes that eventually they'd be able to identify the formation of storms. This group is also the group that proposed doing an International Geophysical Year that was accepted in 1954 to be run in 57, 58. And finally, this group formed the core group of experimenters for what was known as Project Vanguard, which was the U.S.'s first official attempt to orbit a satellite. When NASA was created, that Vanguard team formed the basis of what became the Goddard Space Flight Center in 1960. The Vanguard rocket's first payload, their second successful payload, was also a cloud imager, though not a very successful one. The spin of the satellite was inadequate, and so they didn't get the cloud pictures that they were trying to. But that effort led them led NASA to create what's known as an applications program that was co-equal with its science directorate at the time and embedded in the same organization. It was known as OSSA, for the Office of Space Science and Applications. And that applications program was built really on three legs. One was the development of weather satellites for the use of what was then known as the Weather Bureau. One was the development of communications satellites to be commercialized eventually. And the third was land use satellites. And I've organized these. If I had a pointer, I could show you. Looking at the screen, the Landsat satellite is the satellite on to the right. TIROS was the weather satellite series that Goddard built for the Weather Bureau.
Excuse me. Interrupt you there. Go ahead, Noah.
Yes, we were just both interrupting really quick. It looks like there's some issues on your slides. We're finding some black boxes. I'm not sure if you're potentially on a Mac versus a PC, if that is making
a
difference.
That's it.
But
they look perfectly fine to me, and you're not seeing them, huh?
Gotcha.
Okay. Well, then I guess I just won't talk much about the images.
We'll bear with you on that. So thank you.
Okay.
Yeah, we're seeing partial ones in both the right and left-hand corners. So the Tyros and that's coming out, but the middle of the screen is being blocked. So
it's okay. That's strange. Sorry about that all.
Okay.
But to get back to my story, those three lines became, and plus space astronomy became Goddard's core business. I don't know if you can see this image, but this slide is supposed to be the first real television picture of cloud formations from space. These satellites were derived from a DARPA effort that moved from Fort Monmouth in New Jersey to Goddard when NASA's formed. They flew well into the 1970s. Their purpose was storm warning. They didn't have a quantitative data capability. The real backbone of Goddard's meteorology program became again, I don't know if you can see this satellite, but this was the the Nimbus series of satellite buses. They were research satellites. The deal done with the Weather Bureau was for NASA to build these research satellites to test new quantitative instrument concepts using infrared and microwave spectrum mostly, although later they also developed some ultraviolet sensing instruments.
Eric, sorry to interrupt one more time here, but let's maybe try to, we're getting a recommendation to try to restart the slideshow, and so maybe you can close it and restart it and fast forward to the slide again, and hopefully it'll work, and we'll all be able to see everything. It's just a kind of a black box in the middle of the screen. So we're enjoying everything you're saying.
Okay, so let's see, restart it. Did that help any?
We're still seeing the black box. So, well, that was our best effort, and I'm not sure if other than maybe a non-slideshow mode where we can see it better that way, but of course then we can see the preview.
Maybe the
slides,
folks out there can use their imagination to fill in that box.
And we can provide a PDF in at the end of this too, so people can refer back to it. So we'll just continue on and bear with you. So thanks again, Eric. Sorry.
Well, I'll try your suggestion of restarting here, but restarting completely. Now, can you see the slides if I do it this way? I know they're embedded in my screen, but
it was actually better the other way.
It was actually better the other way. Okay.
Yep.
Okay. Well, sorry. So this Nimbus series satellites were developed to develop quantitative remote sensing instruments for use in future weather forecasting. The Weather Bureau actually pulled out of this program in 1963, but NASA continued to support it into the late 1970s. The picture that you can't see is actually the last of the series, Nimbus 7, which was launched in 1978. Now, the Nimbus program were polar orbiters. At the same time, Goddard invested in instruments for operation in geosynchronous orbit. The key instruments actually developed at the University of Wisconsin under Vern Sumi and Robert Parent, which was a spin scan camera that used the rotation of the satellite in order to make line scanned images of the full lit face of the disk. These were actually tested via experimental communication satellites, and they first flew in a black and white version on ATS-1 and then a color version in ATS-3. This picture, again, I don't know if you can see, is one of the first full disk color images of the Earth ever taken. This and its unflagging support for weather satellite technology is why Vern Sumi is often called the father of weather satellites, and I think is why NASA named an InPost preparatory project satellite for him. The availability of this satellite technology triggered a large number of validation experiments during the 1970s. What was called the Global Atmospheric Research Program was a massively international effort to perform validation and also research on things like the images I showed you for experiment in the Atlantic called the GARP Atlantic Tropical Experiment, which was aimed at both validation and trying to understand atmosphere-ocean surface exchanges. And they set up a network of ships across the tropical Atlantic between North Africa and South America in order to validate the satellite information they were getting from these brand new kinds of sensors. Shortly later, NASA also began to introduce more active sensing techniques. Nimbus satellites had all been passive remote sensing. A satellite called CSAT that's built by Lockheed for JPL introduced synthetic aperture radar, as well as altimetry for ocean surface remote sensing, and a scatterometer to determine ocean surface winds. That satellite unfortunately only lasted about 100 days, but they spent a number of years trying to understand what their data showed, and it became embedded in future satellite efforts. So I've talked a lot about Nimbus. What were its legacies, really? They fostered infrared and microwave temperature profile instruments for feeding weather forecast models in the Weather Bureau, ocean color and sea surface temperature measurements, ultraviolet and infrared-based atmospheric chemistry measurements, and beginning of the use of passive microwave instruments for both sea ice and for precipitation measurements. The Nimbus satellite bus was not compatible with the space shuttle, though. So at the end of the 70s, the Nimbus program was terminated, and so was actually the NASA Applications program, which comes to an end between 1981 and 1982. It's dismantled, and instead, what happens is NASA begins under a law known as the National Climate Program Act to plan a climate research program that goes through a bunch of different names. For a while it was called System Z, it was called Global Habitability, it was called Mission to Planet Earth, and then finally it became the Earth Observing System. And while this was primarily a climate system, the advanced next generation weather instrumentation and weather satellites became part of that new observing system design. And that's what I had for you. I was trying to keep it short so there'd be time for questions.
Thank you very much, Eric. That's great, and it's good to see just the history of that, the satellites. Does anybody have any questions for Eric? And we'll take a couple if you guys want to type any in. Taking a look right now, nothing coming across at the moment. Well, I'll tell you what, Eric, it looks like what we'll do, if anybody does have any questions, we will email them to you. And if you could follow up with an email, that would be great. I really appreciate your time this morning. I know you have a busy day, and thank you for joining us.
Thanks for having me.
So let's go to our next presenter, Dalia Kirschbaum from Goddard Space Flight Center. And Dalia, take it away. I think
all right. Thank you. Now let me just make sure. Are you seeing?
Looks good.
It looks good?
It looks,
all
well,
right.
We had it. It disappeared. Where did it? There we go. Yeah, it looks great.
Great. Okay. Well, first I want to thank everybody from CoCoRaHS for agreeing to have this and supporting this activity. We've had several webinars with CoCoRaHS, and they've always been really great, and so we're thrilled to be participating again. And also want to thank Eric for stepping up. You know, we happened to find his book in the library, no less at Goddard, and say, hey, do you want to come talk about the history? Because, you know, this kind of what he presented is a very nice kind of follow-up to what I'm going to talk about, which is, you know, kind of the current state of how we measure the Earth's weather and climate and hydrology, and what satellites are used to do that. And so the image that you're seeing right here is of the Global Precipitation Measurement Core Observatory right in front. And that was the most recent launch that NASA's had. It was launched a month ago on February 27th. And so I will talk a bit more, or a lot more, about that a little bit later. But again, just want to thank everybody. And the other thing is that there are some videos in here, so if you aren't able to see it for whatever bandwidth reasons, if it appears choppy, all of the slides will be posted, so you can go and look at the videos later. There are these plus a ton more videos to kind of complement the material, and we will go from there. Okay, so let's talk about what we're really studying. So Eric really provided an excellent overview of kind of the early days of how we understood weather and climate and ocean scatterometry, ocean winds, ocean surface, and movement. And so, you know, when we're looking at kind of the Earth as an integrated system, we're looking at how the water cycle is moving, you know, how water is evaporating as precipitation, how it is condensing into form water vapor, clouds, evaporating into clouds and vapor, condensing to form precipitation, running off and going into ice and snow, into storage, groundwater, and eventually making its way back to streams, rivers, and oceans. And so there's a number of different programs at NASA that are dealing with NASA's Earth's water and energy cycles. So this is just kind of listing some of them that either have been flown or currently providing data or will be providing data. So on the left we see kind of the water cycle missions focusing on ice, gravity, which relates to Earth's terrestrial water storage, especially underground aquifers, TRIB, and GPM missions, which I'll talk about more, and then looking at soil moisture and the frozen and solid states of the soil. From the water and energy side, we have missions that either did or are looking at cloud properties, cloud aquifers, etc., cloud profilers, and then from the energy cycle, we have looking at, you know, air quality and climate change, carbon monitoring, etc. And so when we're talking about those, these are satellites that are in different phases of development and are orbiting in lots of different ways. And so complementary to that are some of the kind of geostationary satellites or the polar orbiting satellites on the bottom that you see that are really focused on collaborative missions with other agencies to look at a lot of other things that are important in understanding the total water and energy cycle of our planet. So this is a slightly outdated slide now since we've had a couple new launches, but it gives you the idea not only of what NASA's doing, but the importance of international collaboration. And this is for Earth science missions. So GPM needs to be added to that list, as well as Landsat 8, which was launched a while back. But it gives you a sense of how important it is, not just for what NASA's doing, but in terms of understanding our global water and energy cycle with global participation from other countries. And I think that's a huge component underlying why we can be successful as an agency and why we can better understand what we're doing is because of this international contributions. Sorry that beeping if you're hearing it. Okay, so let's talk about something that's a little bit closer to what I do, which is looking at precipitation. And so, you know, building off of kind of what Eric presented, there's a mission that was launched to look at precipitation, really focused on understanding global water and energy cycles through observing tropical rainfall, hydrometeors, which are actually like raindrops and snowflakes and ice crystals, and latent heating, how heat is released when water is evaporated and condenses. And so just to give you kind of, since we're talking about history a little bit, the Tropical Rainfall Measuring Mission was first kind of conceived as an idea all the way back in 1981, where we talked about, you know, NASA put out a report about the importance of understanding precipitation from space and how we might be able to do that. And so as we kind of step through time, in 1987, the concept of TRIM was proposed, and then going to 1988 was the first kind of preliminary report of what TRIM was. And so TRIM is a very unique satellite, which I'll explain why, and obviously I'm a little bit biased, but it is a pretty remarkable tool to look at global precipitation. And it has a lot of different instruments on board. I'm not going to list them, but you can see them listed at the bottom here, different ways to look at precipitation in microwave frequencies. So looking at it both actively, looking at a radar, sort of like you send out a signal with a police radar gun, you get a signal back, and that's how you can determine how fast a car is going. Well, the similar concept is used using microwave energy for understanding precipitation structure. There's also on TRMM a lightning imager as well as a visible and infrared scanner. And so what the amazing thing is just to give you a concept of how long these missions take to come to fruition. You know, the ideas were first proposed in 1981, and TRMM was launched on actually Thanksgiving Day, November 27th of 1997. And so making a mission and conceiving how it comes from initial science ideas all the way through to becoming an orbit is an extremely long process, both from the science side and the engineering side and technical side, to really get these to a point where they will do their job in space. So TRMM's legacy is firstfold. It was to look at the tropics. How much is it raining in the tropics? And you know, we have so few rain gauges over the Earth. And you know, the citizen science networks that are part of CoCoRaHS are doing a phenomenal job to really report on the precipitation in the U.S. and the general region. But what about over all of the oceans? You know, right now, one of the calculations, it was a paper actually that was just submitted. If you take all of the rain gauges in the world and you put them together, they only fit into 2 basketball courts. So that gives you an idea of how little we're talking about in terms of area with coverage. Now we have radar, ground-based radar, that can give you a little bit bigger picture. But again, if you look over all of the world's ocean, the radars don't extend very far. And so having satellites to estimate precipitation and how it changes, what you're seeing in the top image is actually how much rain we're seeing in the tropics to kind of subtropics. And so that gives us an idea of really this really intense band of precipitation that's along the equator, and it moves based on what season we're in. It's called the Intertropical Convergence Zone. So we get a really good understanding of these bigger term processes. And kind of one of the new things that came out of that was in the middle you see all of these different swaths, they're called, from satellites. And what later, after TRMM was launched, what they realized is that you could actually put them all together and get a global or near global, about 50 degrees north to south, picture of precipitation in near real time. So we're talking about 6 to 12 hours after these measurements are made. You can use a combination of satellites, both TRMM and others, to kind of piece together this picture of rainfall. And it gives us a sense of how storms are moving over the world's oceans and over land. And so we can see where storms are going. So one of the things that I think was not really well understood when TRMM was first conceived as a mission is the amount of information that would be used for understanding hurricanes and hurricane prediction. So this is an example of tropical Hurricane Sandy, which I'm sure all of you have heard of. It took place in October 2012. And so the big image shows the accumulated rainfall from this kind of pieced together image of TRMM. And it shows that actually the highest precipitation totals, which are in red, are actually off the coast of the U.S. And the white shows the eye of the storm. But what amazing thing is in the image that you see circulating, hopefully, and if not, you can always click the YouTube video and see that, what the precipitation radar on board TRMM was able to do is layer by layer look through these storms and see the structure of the precipitation in 3 dimensions. Now, that's the first time we've ever been able to do that, and the reason that it's so amazing is because you can see these types of internal structures down to kind of the individual raindrops in the layers. You can actually get a sense for how the storm is intensifying and where it's moving. And so for understanding storms like Hurricane Sandy, that's really, really important because the weather forecasters and the hurricane modelers need to know where to make evacuations. And so TRMM is a huge contributor to understanding these tropical processes, not just in the bigger scale, which is what it was initially thought, at the monthly scale, but actually in real time at a very, very detailed level, like we can see 3-dimensionally through the clouds. And so as talking about the evolution of what we can do with data over time, TRMM is a really amazing example of how we can take a mission's concept and evolve it to meet the needs of what society has. And so one of the things that is noted is that TRMM is in a tropical orbit. So it's called a non-sun synchronous orbit, and it only goes from the 35 degrees north to south. So the northern limit of the TRMM extent is shown in this black bar. And so what that means is that we're actually not able to see the precipitation from the TRMM satellite as it goes beyond that point. We kind of piece together the data from other satellites in the area and tried to calibrate it so that it has kind of a uniform picture. So that's where GPM comes in, the Global Precipitation Measurement Mission that was just launched. Now, this is a video, again, if you can't see it or if it's blocky, no problem, I'll describe it, but definitely take a look. So what we just saw was that TRMM orbits from 35 degrees north-south, and GPM is actually orbiting now from 65 degrees to 65 degrees, which is about the Arctic to the Antarctic Circle. And the other unique thing about this satellite, and I'll talk about the instruments in just a second, is that it works with other satellites internationally as kind of the anchor to create a global precipitation data set every 30 minutes, actually, or with a latency of about 3 hours. So within 3 hours, we're going to know how much it's raining and snowing everywhere around the world. And so you can imagine how powerful that is when in the northern latitudes, for example, where we don't always know how much snow is falling or light rain. And those are huge contributors to freshwater resources. And so to get a better understanding of everything from light rain to heavy rain and snow, we get a better sense of the water cycle and what our planet is doing. And so just a little bit about the instruments, and then I'll get into kind of how we built it. So the instruments on board the GPM core are similar to that of TRMM. It has a dual frequency, or two different frequency precipitation radar, similar to TRMM but double, and it gives you that three-dimensional structure, kind of like a CAT scan of the body. And so the other instrument is called a microwave imager, and so that, or GPM microwave imager, and that's sort of like an X-ray. And so together, these instruments are really powerful in helping to diagnose how much precipitation we have at any given time. And so by providing these most advanced instruments with a series of other satellites, about 10 in this constellation, we can get a continuous picture of precipitation, and it's calibrated by the GPM core satellite. So if you think of it sort of like a lead violinist in an orchestra or another instrument, they play a note and it helps to kind of give a standard sound for the orchestra, and that's sort of what the role that the GPM core plays. Now, the reason that we're so excited about TRMM and GPM is one, it was developed in-house at NASA Goddard Space Flight Center, but it's also co-led by NASA and the Japan Aerospace Exploration Agency. And that partnership existed for TRMM and for GPM as well. And there's been a long series of these partnerships, not only with JAXA, but with other international space agencies around the world. So this just gives us an idea of some sample testing that was done in the top and kind of sides, showing the satellite in development and the amount of time and technical expertise that is needed to really put the satellites through its paces to make sure that it's ready for space. So just two examples: electromagnetic interference. It sends different electromagnetic signals at the satellite and makes sure that the instruments can perform correctly. And vibration and acoustic testing, which basically shakes it and pumps it full of sound to make sure that the satellite can withstand the forces that it experiences on launch. And then the thing that's in the middle right is showing the satellite that's actually, which is all the different colors, put inside this huge thermal vacuum chamber. So they pump out all the air and they make it hot and cold to simulate how the satellite is going to experience both heat and cold, solar radiation, and the cold side of the spacecraft when it's in orbit. Now the satellite was, as I said, the satellite was developed at NASA. The instrument, the radars were developed by JAXA, and the microwave imager was developed by Ball Aerospace in contract with NASA, and it was assembled and tested at NASA Goddard Space Flight Center here in Greenbelt, Maryland, and then it was actually shipped. What you see in the bottom left is it was put in a really intense shipping container and put in the largest aircraft the Air Force has, a C-5 Galaxy. It was put there and sent over to Japan, where it was launched. So I am hopefully going to show you the launch video. Again, if you can't see this, no problem. The launch is on the SBS gallery. So this is all in Japanese, so I'm not going to translate because I can't. But this is on an H-2A rocket. And what you see is the pools of water are actually, there's so much explosive power with the launch that they need to kind of buffer the sound. And so this was what we had about a month ago as the satellite launched from Tanegashima Space Center down in the southern part of Japan. And so this was an excellent launch. It actually, I think we can now say that it went exactly how it was supposed to. The satellite was deployed at its 407-kilometer orbit, which is sort of the distance between New York and Washington, D.C. And I'm very, very happy to report that we just received the first images. They went public on Tuesday of what the satellite saw. And so the first images, they're called First Light, was actually the storm that happened on March 10th, an extratropical cyclone that passed to the northwest or northeast of Japan. And what was interesting about the storm is it contained heavy rain and snow, and it's the first time that we've ever been able to see an extratropical storm in 3 dimensions over the oceans. And that's relevant because we want to understand how these hurricanes change as they move northward or poleward, I should say. And we haven't really been able to do that in 3 dimensions. So having this type of information is really key to really understanding these intense systems and how they both affect, intense rains in the tropics all the way to the extreme snow that they actually generated over parts of Japan. You can actually see kind of the snow-covered Japan in the top image in the northern islands. So the bottom images on the left shows the radar, the 3-dimensional structure, and on the right shows the 13 different channels that the GPM microwave imager has, and they're sensitive to different types of precipitation, so they're able to see the difference between rain and mixed phase, rain and snow, and snow. And so we're really, really excited about where this is going, and GPM continues to provide really great imagery. But I'll take my skeptical hat on in a second and say, so what? Okay, we have a new satellite that can measure precipitation. It differs from the weather satellites that you see in that it's a different orbit and it's much lower. So it's able to get really detailed measurements of precipitation in a way that the weather satellites, the geostationary satellites sitting at 22,000 miles up, really can't do. But in terms of the applications, how NASA data can be used for different purposes, both societal and science. This is just lists some of them. So talking about extreme events and disasters, water resources and agriculture, weather and climate, and modeling, and public health. And I'm going to get into a couple of these now in terms of kind of the bigger picture. So the topic of this webinar is observing our blue marble. And so I'll talk about some of the other satellites we have as well, but I'm just giving some examples from Precipitation Now to show kind of the breadth of the applications that these types of satellites have in understanding not just like our weather and climate, but everything down to agricultural resources and even disease tracking. So first to talk a little bit more about hurricanes. Again, this is another movie. If it's blocky, don't worry. You can see it another way. But this is an example of the Hurricane Katrina. And this is an image from TRMM. And what happened was TRMM passed over Hurricane Katrina when it was intensifying in the Gulf of Mexico. And so what you're seeing, these big red towers are actually called hot towers. And these huge convective towers that are indicative potentially of how storms may intensify. So when you have this really intense convection, it indicates that the storm might be getting ready to get bigger. And indeed, this is what happened. Less than 12 hours after this image was taken from TRMM, the storm did unfortunately intensify and it made landfall, as you all remember. Now, getting these 3-dimensional pictures off the coast are critical to understanding kind of the intensification processes of this storm and understanding, not just with TRMM, but as we saw even with GPM in this first image, seeing how this storm changes, such as Hurricane Sandy, from a tropical system to an extratropical system is huge for understanding where we might have the most intense rainfall or coastal flooding and even high winds when you transition it to kind of the intensity of the storm. So another example that is extremely topical, unfortunately, is the ability to use precipitation data and other satellite observations to look at landslides. Now, a week ago, I tend to kind of talk about landslides, which is my area of expertise, and kind of move on. But, as we saw in Washington, this extremely catastrophic and unfortunate landslide happened, not even a week ago, Saturday, March 22nd in Oso, Washington. And so this landslide, from what we understand now, was really a function of weakened soil to begin with. It was based on glacial deposits, and there was previous landslides in the area, but it also had been a really wet season. And so the graph on the bottom shows the data from the TRIN satellite, the Tropical Rainfall Measuring Mission, over the past 14 years or 15 years. And so what you can see, this is the cumulative rainfall from the start of the rainy period each year from 2000 to 2014. And so the blue squiggles show all of the other years, and the red is this year. And so what probably jumps out at you is, one, when you get till the end of that series, it's pretty high up there. It's actually the third wettest season that was observed, and the wettest season at that location since 2004. But the other thing that you notice is there's actually a pretty steep increase as you get into February, where there was a lot of rain kind of leading up to this event. And so what I think is what they're looking at is that their rainfall is by and large the most significant or most frequent trigger of these types of landslides. And so while in this case, this catastrophic case, we don't know, it's really, really difficult to predict the actual timing of the event. But by being able to diagnose the variables that might be contributing, is it a wet season? How steep is the slope? In the top right is a picture from Landsat taken the day after the landslide, and it shows the extent of how it was blocking the river. Is it a 15-meter resolution? So you can kind of get a sense of the sheer magnitude of the event. By being able to piece together all of these different assets we have, both satellite and non, we can try to get a better sense of where and when these events may happen. Okay, another topical example is looking at drought in agriculture. So this is the drought monitor I actually just pulled today, and the projections for intense drought in the U.S. And this is done by the drought monitor, the URL. So on the left, you can see these areas of red and dark red, and that indicates areas of extreme drought or exceptional drought. Now, these drought monitoring tools in agriculture are based on a lot of different variables, and one of them is understanding precipitation and the health of the soil, or the health of the vegetation. So if you look on the right, this is an example of an estimate taken from the MODIS image, the MODIS instrument on board NASA's Terra and Aqua satellites. And what it can do is it can actually look at the signal that the vegetation is giving off and be able to tell over time if the vegetation is healthier or not as healthy. So brown is less healthy, and blue is healthy vegetation. So you can see when you compare both these models, which is what's on the left, with images on the right, it really helps you to diagnose what we might anticipate kind of moving forward with weather and climate modeling, and also what we see now. How has the vegetation physically changed? And so that's one way that we've been able to kind of look at this crisis in addition to lots of others. And so another example, we're getting to weather and climate. This is the top image is a cross section of a hurricane. You can see the eye, if you kind of take a slice through it, you see the eye, which tends to be, pretty non-cloudy, and the eye wall, which is the most intense precipitation. And so having this data really helps us to, such as three-dimensional pictures like we have with TRIM and GPM, helps us to try to diagnose what's happening with these storms. And then if you go to the bigger picture, if you think of weather as our mood and climate as our personality, we need to have these long-term records of how our climate is changing. The images, the graphs you see here are showing precipitation, and the brown areas indicate less rainfall over time in looking at this past decade, and blue indicates more. But there's a lot of white areas on this map. And what the white areas indicate over land is that we really don't know what's happening. And so the key is that we need to have this long-term record of precipitation and all these other climate signals to get a better sense of what's happening. And then just one other example is, I think, is talking about evaporation. So weather is a consistent system. It's coupled to how the Earth is responding. So this is an image from Landsat, which is there's a series of Landsat satellites. They're NASA and USGS-led missions. But there's other channels on Landsat that can give you surface temperature and evapotranspiration. And it turns out that understanding how evapotranspiration plays into understanding how weather patterns change is very significant. Now, I know that there's a number of the CoCoRaHS community that's looking at evapotranspiration, and so we've talked about precipitation a lot because that's one of the things that we're focused on with TRIM and GPM. But there could be possibilities of being able to use the citizen science data that you are taking of evapotranspiration to mapping that to some of the satellite imagery that we have from Landsat, for example. And so this is an area where it really underscores the importance of a coupled system between both the surface and the atmosphere. Another example, kind of going subsurface, is GRACE. And GRACE is just a really cool mission because it's been up for a long time, and it has 2 satellites that basically use Earth's gravitational pull. In areas where we have high mountains, you can actually see with this rotating globe, you can see it, high mountains are red and kind of less gravity is in blue. And so once you take away all of the main features of the gravity with like the big ocean, mountain features and the like, you can actually find out where there are big aquifers, underground aquifers. So just to give 2 examples, one is looking at the Ogallala aquifer out in the west part of the U.S., and also looking at northern India. And so they can actually observe these systems changing because of these gravity measurements that they have. It just kind of blows my mind a little bit that you can do this and look at Earth's water resources with a gravity mission. And again, there are a lot of different purposes for this, and the second series of GRACE looks like it's going to be launched sometime in the 2017-2018 region because of the importance of what we found in applications of this data. Okay, so the other thing that I wanted to bring up is that GPM is actually the first of 5 missions, Earth science missions, going up this year in 2014. And so it's a really big year for Earth science and being able to keep our eye on the blue marble, which is really exciting as an Earth scientist. And so GPM, I definitely recommend going to the Earth Right Now website to get a sense of what we're talking about, but I'll give you a preview. So GPM, again, was launched on February 27th, very successfully from Japan. And then a mission set to launch in July is called the Orbiting Carbon Observatory, OCO2. And so it's going to be the first dedicated remotely sent satellite to study atmospheric carbon dioxide. And it'll be able to characterize where the carbon is going, where it's coming from, how it's moving on the regional scale, and also look at how we can anticipate it over seasons. The next 2 are launching in August and September, and they're going to be instruments placed on the International Space Station. On the left is called Rapid Scat, and that is, Eric mentioned about a scatterometer earlier in the talk. This is replacing QuickScat, which stopped providing data in 2009, and it's going to look at ocean surface wind speed and direction. And then the other instrument is called CATS, the Cloud Aerosol Transport System. And NASA loves acronyms, so if you haven't figured that out already. And so it's going to be looking at the composition and distribution of pollution, dust and smoke, and aerosols. So clearly this mission is linked to precipitation measurement missions, as we're looking at, CATS looks at finer particulate matter, but things that water vapor likes to glom onto and create precipitation. And so going forward, understanding kind of where we're getting these pollution and dust and smoke and aerosol plumes and evaluating that with precipitation is something that is already ongoing research, but something we also look forward to evaluating moving forward. Sorry about this. Okay. And then the last mission set to launch in 2014 is called SMAP, the Soil Moisture Active Passive Mission. And so it actually uses both active and passive technologies to look at the state of the Earth's soil, both in terms of soil moisture and its freeze-thaw state. And so it really helps us to understand everything from energy and carbon cycles and storage, water, and even going down to weather and climate models. You know, we talked about with evapotranspiration and temperature, you know, it's a coupled system. So where it's warmer, there's air rising, you have more condensation with precipitation. Where it's cooler, you potentially have higher pressure centers, so there's air that's sinking. So it's clearly linked, and so all of these missions are designed to look at different aspects of weather, climate, and hydrology, and how that factors into the Earth's water cycle. So with that, I'm actually going to end, and I am very, very happy to take any questions, and I think I'm going to stop there.
Thanks, Dahlia. Really very informative presentation here. I really appreciate your help there. We've got with us, and actually I can hear him talking in the background, is our director, Nolan Duskin. And Nolan might have a couple of questions for you to start things off. Before I go to Nolan, though, I've got a question that's come in. And if any of you have questions out there, go ahead and type them in now, and Dahlia will be glad to ask them. Lloyd from Palmyra, New York, wants to know how the size of the GPM satellite compares to previous and future satellites. So how big is it? You know, we could kind of get an idea from looking at the pictures, but how does that look compared to the old ones and the new ones?
Yeah, so great question. So GPM is actually quite large. It is about the size of I would say a small corporate jet, tip to tip, or if you think of like a small school bus. And so it is the largest satellite ever built and assembled at Goddard to date. It's larger than TRMM, which was the second largest satellite built and assembled. So so if you can imagine, it's pretty large in terms of its wingspan. And the weight of it I have somewhere, but I can't find it now. But it has about 550 kilograms of fuel fully loaded, and the hope, and since maybe this would come up anyway, I'll just answer the question now. TRMM was a science mission that was designed for 3 to 5 years of lifetime, and it's lasted for a number of reasons. It's lasted for it's going on almost 17 years. Now GPM is larger, and there's some restrictions based on how big of a satellite it is, but it's also designed for 3 to 5 years. But as I said, there's a lot of fuel on board, and with the solar panels and fuel to maintain its low Earth orbit, we're hoping that it extends beyond a decade. And so because there's right now an overlap between TRMM and GPM in terms of data collection, what we're going to be able to do, and this actually matters for citizen science, is we're going to be able to reprocess the entire data set going all the way back to when TRMM launched and get one continuous record of precipitation that then can be compared to ground-based systems over time and get a much better understanding of precipitation both in our country and around the world.
Thanks. I've got some other questions coming in. We will list, we'll put some of these URLs, Dahlia, if you can send me a list of ones you think folks would be interested in, we'll put those on our webpage for folks to look at after the presentation. We'll hopefully have them up this week. Here's a question from from Jeff, and Jeff would like to know, how long does it take for data to become available to NASA and ultimately the public after each satellite is launched?
So the instruments on board GPM are currently in their checkout phase. The satellite has been putting through the paces. They're testing the thrusters and the star trackers and everything, rotation wheels, as well as the instruments. So as you saw, the first data is out, but right now it will be going through a 60-day checkout period, and the data for the public will be available about 6 months after launch, so probably about September. And this merged product, which is kind of this integrated product of all of the satellites together, takes a little bit longer to develop. I can go into the details, but I don't know if you guys really want to know that. And so that'll be hopefully coming out within a year of launch. But the idea is that right now, TRMM data is freely available in a lot of different formats. There's Google Earth, there's GIS, there's lots of different formats. So for anyone that wants to play with the data, we can give you the links to play with TRMM data, and GPM data will look very similar, just slightly better, hopefully.
Thanks. I've got a question for you. You talked about the landslide that happened this week. How common, just common, are landslides like that around the world? How often do we see them? I know this took a lot of lives, so it really, it's made the news. But do these happen often, or is this a rarity?
Well, I think a landslide of this magnitude is rare, but I think what's important to note is that these types of catastrophic landslides happen every year, frequently multiple times a year in different places around the world. We just tend not to hear about them as much because they take place in the Philippines or Nepal or Indonesia or Africa, Uganda. Now, this landslide in the U.S. history is probably one of the worst that we've had in most recent decades. The most recent catastrophic landslide we had was in California, and that took place in 2005, and it killed about 10 people, and that was also a reactivation of a previous landslide that happened 10 years before that. Now, an interesting thing about this landslide, and you might have heard already on the news, is that there was a pretty significant landslide in 2006 in this exact location, and so understanding these triggers, where we have steep slopes and rainfall, and where that all comes together at, unfortunately, the right time is where we get these triggers. And so if you think about everywhere around the world that has a lot of rainfall and a lot of topography, think about the Himalayas, Nepal and India, think about the Philippines, Indonesia, Japan, parts of China, Central America. These are all hotspot regions for landslides, including the west coast of the U.S. and the Rockies, as well as the Appalachians. Now, to make a long-winded answer of a short question, landslides happen all around the world, and they actually kill thousands of people every year. We've been keeping a catalog as best we can, and so this is just one unfortunate incident that really hit close to home.
So they can happen on the East Coast as well, in some of the Appalachians and stuff. Where it seems like a lot that we hear about landslides, California, the West, but I guess they're common there as well. Is that right?
Exactly. So if you look, think about the Appalachians are kind of a older mountain range, and so a lot of the newer mountain ranges, where tectonics are still active, you're still having active uplift or change. There's a lot of active weathering that goes on. Landslides are just a natural weathering process. It's a disaster when people, unfortunately, are in the way. And so the Appalachians, the Blue Smoky Mountains, they all have landslides that are frequent. They just tend to be shallow or small, and so oftentimes they aren't really reported where they don't affect people.
These are kind of like avalanches, I guess. The time to get out of there's really not much time to get out of the way once they start, right? Is that there's no warning, or you just got to, if you're there, you're kind of sunk.
Well, there's all different types of landslides. So they have slow-moving creep landslides that can take years to kind of move, and those tend to be kind of well-monitored areas in the developed world, and so they're able to kind of observe it and obviously move out of the way. But there's the rapid flows, such as the one we saw in Washington. You're dealing with a catastrophic failure. It's called a rotational slide. But because there was so much water in the soil and in the river below, it really mobilized this huge runout of mud and rock and debris. And so that was the most critical catastrophic point of inundating 49 houses. So it really depends on what you're talking about in terms of the material. So rock avalanches too. If it's rock, if it's snow, usually those are fast moving. Whereas if you have a really slow moving landslide that's kind of just gradually moving over a season, it might not be as big of a deal.
Thanks for letting us know more about those. And Dahlia is an expert on those, so really great to have you able to talk about this timely thing. We've got a couple of questions coming in. Let's go back to the questions from our audience out there. David writes, how many receiving stations get the data from these satellites, and are they run by countries that they are in? So I'm not sure about the second part of that question. Are they run by countries they are in?
Yeah. So, I'll answer the question that I know from TRIM and GPM. Now, TRIM and GPM use what's called the network of TDRS satellites. It's the Tracking Data Relay Satellite System, I believe. And so what that is actually a network of satellites that are sitting above the Earth, and they are always in constant communication. And so everywhere that GPM and TRMM orbits, they're always in contact with one of these TDRS satellites. And so what happens is the satellite keeps sending this signal, and it gets bounced off of these different relay sataelites until it hits the ground station, which we have, which is in White Sands, New Mexico. So that data gets moved from White Sands, New Mexico, back to Goddard, where it's processed in the building right next to mine. And that process happens, I'd say, within 20 minutes. So it gives you a sense of how quick that process is of getting from data from satellite all the way down. And some of the data products are available to users within an hour after the data has been obtained by the satellite. Now, some of these other satellites, like polar orbiting satellites, for example, SUMI, NPP, they have different downlink stations in different areas, and other satellites are have downlink stations all over the world, and so I'm not as knowledgeable about kind of who does downlinks where, but it depends on the type of orbit that the satellite is in, and it depends on the frequency of the downlinks. So some satellites have a faster frequency of downlinks than others.
Thanks. So Cindy has a question, and she wants to know if you can explain how the gravity measures can help detect groundwater. What is the connection between the gravity of an area and the amount of groundwater? Can you go over that a little bit?
Yeah, it's not my area of expertise, but I think it's so cool. So if you see the picture if you're looking at what I'm looking at, which is Grace, so there's two little they're two satellites that are constantly in contact, and they can measure so as the two satellites that are flying in tandem move over an area. So picture the Himalayas, right? It's a huge feature, and because there's so much rock that's sticking out of the ground in these mountain ranges, it creates a stronger gravitational pull. And so because when the satellites together move over the Himalayas, there's this very, very slight pull of gravity that's different than other regions that actually pulls the satellites together. And if they can measure it to, like, I think like a couple cells. I mean, like a human hair is way bigger than what they can measure. I mean, it's very, very detailed measurements. And so by being able to, continuously over time observe how the satellites either move together or move apart based on the Earth's pull of gravity in different places, you can get a sense of kind of these big features that you see sticking out on the globe. Now, what you do is, in order to get what's happening under the ground, these huge groundwater aquifers have the same type of gravity features that, big mountain ranges do, just they're very slight. And so if you remove all of the signals that we know about, mountains that don't really change that much, you can actually get a sense of where these underground aquifers are, because they have different gravity signals than the Earth around it. And so that's how they've been able to see over time and over large areas how these sources of like aquifers are actually changing.
Related to this question, Chuck writes and wants to know, Chuck from Oregon, does GRACE give a good indicator of total water available to the Earth's inhabitants? So,
it's I think that it's a question of, how can we understand Earth's water budget? We only have a finite amount of water. The water that we have now is the same as the dinosaurs had, is the same that our great-great-grandchildren are going to have. And so understanding not only what's in our Earth's aquifers, but how much is stored in snowcaps, how much do we have in our rivers. I really think that while GRACE can provide a really cool idea of what's happening under the ground, it really takes a network of satellites looking both at the atmosphere, at the surface, and at the subsurface to get at that big question. And we still don't have a 100% answer. I think the reason that we're sending 5 different missions up this year for NASA is that we're trying to get at how much water we have, where is it, how is it distributed, and how is it affecting our climate and our lives. And so I think that it has to be multiple satellites providing this picture.
Thanks. We've got a question from...
Sorry.
No, that's all. Go ahead. Go ahead. Michael has a question for us, and he wants to know that can the instrumentation on these satellites be changed or updated after the decision to proceed with the satellite is made, and is it ever done? So,
no, I've definitely gotten that question before. There comes a point in the engineering development of the satellite, of the instruments and satellite, where you can't change it, and so the instruments are designed a certain way. But the thing is that while the instruments, once they're launched into space, and even when they're being finalized, while the instruments can't change themselves, the software can change, and so frequently there's software upgrades to the system, which allows the satellite instruments to potentially do new things. Or once a satellite takes the pictures or images or whatever data it's obtaining, the satellite data can be used to understand new things. And so while we can't change the instrumentation in the hardware itself, we can actually change the software to some extent and get new answers to questions from that ability. So I say it's in the software.
So it would probably be cheaper to send a new satellite up than have somebody go up there and put a new camera on one or something like that. I would imagine.
Well, Hubble's a very
speculating.
unique case. Yeah, I mean, and this is out of my area of expertise. Hubble's a very unique case of a resurfacing mission trying to actually fix Hubble or change it. The International Space Station is an amazing international platform for adding those types of instruments. So they continually add instruments to the International Space Station to do tons of things, from look at the galaxies to look at the landslides on Earth. So I think it really is. Satellite missions are not cheap by any stretch of the imagination, but there's a lot of different ways to look at these processes. And so the goal of NASA and all the other agencies that use satellite assets are to expand the bounds of what we understand and try to keep pushing the realm of what we don't know to get a better understanding of both our universe and galaxies as well as our home planet.
Okay, a couple more questions coming in. Sean writes, and he says there's a lot of data from many of these missions. What are some of the best ways that someone interested in this science can keep up with what's being observed and discovered? So how can they keep on top of what's going on?
I think one of my more favorite websites for NASA is called the Earth Observatory website, and I'm happy to send that out. But if you go to NASA Earth Observatory, you can see that. They feature a ton of different Earth science missions and images and talk about specific features. So I think there was a landslide probably story up there about the Washington landslide already. If not, it's coming. And so I think that to just kind of be in the know of new things that are happening, specifically with Earth science, the Earth Observatory does a really great job of talking about that in ways that people can kind of relate to more than just posting an update on a mission. But the NASA.gov website also has all of the different updates, press releases of things happening, and there's also really active social media. So if you follow NASA, if you follow NASA Goddard, or if you follow GPM at NASA_Rain, that will have the Twitter updates and Facebook updates will also kind of feature the newest, greatest things that are happening. So social media and the Earth Observatory, I think, are the best places.
Great. We've got another question from Cindy, and she wants to know, how does microwave data give the 3D precipitation map of storms that you showed?
So it's a great question. So well, they're all great questions. Sorry. So if you think about the visible spectrum, and we can see different colors based on their wavelength. So we see the difference between red and green and blue based on what wavelength it has to our eyes. Now, precipitation is radiating in a microwave frequency. So rather than visible, they're in microwave, so it's longer wavelengths. And so because precipitation gives off different frequencies of microwave energy, the kind of passive systems can absorb that and be able to tell the difference between the signal that's given off by light rain, by heavy rain, and by snow. Now the active systems actually send out a microwave signal, a very, thousands and thousands of pulses per second to the ground below in a certain swath, and based on the scatter back of that signal, that microwave signal, off of the precipitation themselves, it actually can tell you both the size of the precipitation particle, so is it a raindrop, is it a big raindrop, a small raindrop, a snowflake. It can tell you about the type and the distribution. And so by being able to understand kind of those physics all the way at the very, very small scale, layer by layer through the cloud, getting that back signal from the active microwave signal sent out by the radar, we can tell the difference of how the storm is changing layer by layer through the clouds.
Okay, thanks so much. I'm going to ask anybody on the CoCoRaHS staff that's on the call right now or on the webinar, do you have any questions? I know some folks might. And
Henry, can you hear me?
Oh, there's Nolan. Hey, Nolan, welcome. Nolan is our CoCoRaHS director, our state climatologist, and
I got about 6 hours worth of questions.
6 hours. Wow, we're gonna have to expand the webinar. But go ahead.
No, I'm just whenever you see presentations like this, you start thinking, well, why in the world do we need any rain gauges anyway? They can see everything from space, but when you really get into it from the other point of view, you find out that no, they are measuring what they're able to measure from space. It's not a direct measure, it's very much of an indirect measure, and then through amazing algorithmic science-based assessments that are literally based on years and years and years of research by many, many scientists, you're able to come up with relationships that estimate rainfall based on the things that you can measure. I'm super curious if we were to, 10 years from now, with GPM data, if we were to draw a map of U.S. precipitation based on satellite only, and then compare it with our ground observations, how similar or how different will it be and why?
Yeah, I'm so glad you brought that up because I didn't talk about ground validation at all. And usually I do when it's a presentation kind of talking about GPM as a whole. Ground validation or kind of ground truthing by citizen science, by rain gauges, by radar is fundamental in connecting the dots between what we observe on the surface or the actual surface precipitation to what the satellite, as you're saying, is seeing, but not as an actual, it's not a rain gauge in space. It's actually measurements of brightness temperatures or microwave information that we're getting that computer models, computer algorithms translate to what we know as precipitation on the ground. And so having that connection is fundamental to improving and continuing to improve the ability of satellites to see or estimate precipitation. And so one of the things that we're doing, and I'm going to try to answer your question, but I wish I had a crystal ball, but I don't, is that there's a series of field campaigns that look at different types of precipitation, be it, falling snow in Canada or light rain in Finland. We just had a field campaign over Iowa to measure floods, and actually we had a CoCoRaHS webinar on that topic. And we have one coming up in May and June to look at mountain precipitation and hydrology in North Carolina, in the Smoky Mountains, actually. And so those types of kind of concentrated field campaigns are really important for understanding and kind of connecting the different types of rain processes to the satellite the satellite data that is collected. And so as part of that, we have a network of gauges around the world, and we have a network of radars that's used to validate. But the thing that we're continuing to look more into is the role of citizen science and the role that we can play with the power of the community in saying, maybe not how much did it rain down to, the closest tenth of a millimeter, but is it raining, or how much is it raining, or what sense are we getting for how well the satellite is doing? Because a lot of the times there could be, well, not a lot, but oftentimes there can be challenges to areas like mountains and coastal regions. So where I can't say how much things are changing and how much better the satellite record will be in the future relative to the U.S. ground-based precipitation estimates, I can say that we are definitely moving in the direction of merging ground systems with satellites to try to get that picture not only over the U.S., which is has a wealth of ground-based systems, but over developing countries, over the oceans, over places where we have absolutely no ground-based systems. And so I think that's where the power of GPM really can come in. But again, ground validation is critical to really improving the satellite signals.
And you're really telling us don't quit measuring precipitation.
Absolutely not. In fact, I have a colleague, Kristen, here with me. She just met with 43 different teachers around the area here there's 43 different teachers who all now have CoCoRaHS rain gauges and are in the system to continue the monitoring effort and to feed back into CoCoRaHS. So we are extremely active in trying to promote citizen science, both through CoCoRaHS, through a web development that was recently done with somebody else, with the National Weather Service and Oklahoma. And so we're kind of trying to push the boundaries of getting these data collected and also how we can use that data to improve our validation from the science side. And that's an active area of work that we're currently in.
We have another question coming in from one of our viewers or our audience right now. What is the optimal altitude of weather satellites, or does it vary? So what are you got your geostationary and your polar orbiters, two different heights.
Right. Yeah. Well, geostationary and polar orbiters and non-synchronous orbit. It all depends on the instruments. The low Earth orbit that GPM is in and TRMM is in, which is like about 250 miles above the surface, is different than the polar orbiters, which are in like an 800-ish kilometer altitude. And so it really depends on the instruments that are on board and what their purpose is. And so all of them have value and a specific reason for why they're in the orbit they're in and the data they're able to collect.
Okay, well, I think we're coming up on about 15 minutes past the hour now. We're going to wind things up for today. If you have any other questions, I'm sure Dahlia would be glad to answer them. If you send them to us, and we'll send an email to her. I really appreciate you taking time out of your busy day, both you and Eric, today to be with us. This is really very important information to get out there, and we really appreciate your time, and it was a great presentation.
Well, thank you so much. And I actually saw in the chat window there's a question about the basketball courts. So the basketball courts, the rain gauge basketball court kind of analogy is based on the operational rain gauges around the world that are used, that are kind of the part of the World Meteorological Organization and others, like active rain gauges that are functional. It doesn't include citizen science rain gauges. So I'm sure if we put all of the CoCoRaHS rain gauges and all of the other rain gauges that are kind of used for other purposes, I'm sure it would be bigger. But
yeah, I did some calculations while you were talking about that earlier, and if we base it on about 20,000 rain gauges out there from our citizen scientists, we're a little bit a mile by a square mile. So yeah. It's a pretty good size.
I question that calculation.
I know, and I cite it only because they just published, I think a paper is in press on that, and it's really funny because every time I give it, all the scientists in the room start scrabbling on the back of the paper to kind of calculate it. But based on the definition, which is operational rain gauges that continually report, that's what they got, and that's actually less than that. But I can refer you to the publication because I was skeptical too. But
it's really amazing. Yeah, it's really amazing how well we're able to sample patterns with very small sampling areas. So
exactly,
that's really neat. Thanks for sharing that.
Yeah.
Well, I'm going to remind our folks out there, and again, thank you for your time today, to take the survey at the end of today's webinar. We're going to say so long for today. Please join us for our next CoCoRaHS Weather Talk webinar. That'll be, mark your calendars, on Thursday, April 17th, and we will talk about air quality on a local, regional, and global level with Colorado State University's Sonia Krodenweiss. And Sonia works in atmospheric chemistry here. She'll have a really good presentation. Sign up for that one. You can go on the web and do that now. So this is Henry and Nolan and the rest of the crew here signing off for today. Thank you for being with us, and we hope you'll join us again next time. Goodbye.
Thank you so much.